A lot of people have been asking questions about the machine calculations, so I thought I'd do an example. There's a lot of different things that you need to think about that you probably didn't realize that you needed to think about. So in this example, I'm going to do a slingshot type problem because most of you guys are using bands. Something you're going to need to be thinking about is the force of your band or propulsion method. So we have to look back at some of our force activities. You are going to need to be worried about the potential and kinetic energy of your projectile. You are also going to need to think about the velocity of your projectile as it leaves your machine. And then you'll finally be able to go to those position equations that we started this project with long, long ago. So none of these things are new. None of these things are brand new things that have never been talked about before. We've done activities for every single one of these, multiple activities for most of them. So you might want to go access some of your math and physics documents. You're going to find that a lot of the answers are there for you. A lot of the equations and things that I'm using here will all be represented there. All right, so like I said, I'm going to do an example that's more like what a lot of you guys have been doing. Although, keep in mind, it's going to be my example for my machine. Your equations or your calculations will look different because your machine is slightly different. Your numbers will need to reflect what your machine actually does. So most of you guys decided to do a slingshot, so I'm going to do an example for that. If you guys are doing some other sort of catapulting device, there will be a little bit of a difference in your calculations. However, you will still be needing to consider the same things. For forces and springs or your bands that you're looking at, a good document to look at would be the springs and other stretchy things. In springs and other stretchy things, we talk about Hooke's law. Hooke's law is F equals KX, where F represents the force, K represents the distance you stretch the spring, X represents the distance you stretch the spring, and K represents the spring constant. You need to know the spring constant for your particular resistance band. In that document, there's a really good lab setup for you to do that. It talks about gathering some data by using some masses and your particular stretchy thing. So I did one for mine, and I ended up figuring that it takes a force of about 60 newtons to pull my band a distance of 2.25 meters. I want to make sure we're in meters. So now when I find my spring constant, I'm just going to plug these two things in. So I know that 60 equals K times 2.25. So I need to divide both sides by 2.25. So I get K, my spring constant, is 26.67. So that's a number that I'm going to need to use again, so I want to keep that in mind. However, there's one thing we need to go back and think about. I am stretching my band with it folded over. So like if I were to look at it from above, my band is like this, and I put my beanbag here and I pull it back this way. So my band, the data I got was for just a single band, which means I need to double this to represent the fact that I'm pulling using twice that. So when I actually figure out, when I use this number later on, I'm going to need to double it, and I'm going to be using 53.34 as the value in my next calculation. Most of you guys doubled yours as well. Some of you guys quadrupled yours. So you're going to need to keep that in mind when you use this number when you're talking about energy. Which leads me to our next topic. Potential energy. A lot of you guys have a good handle on what potential energy is, but it's a little bit trickier when you're trying to actually find the potential energy of something. Well, in that Springs and Other Stretchy Things document, we talked about how we can find the potential energy of a spring. And so the potential energy of a spring or your stretchy band, is 1/2 that spring constant times x squared, where x is that distance that you pull it. So for my particular machine, I can fill some of this in. I know that my potential energy is going to be 1/2 times 53.34. That's the number I got on the previous slide, and then it's doubled because I'm basically using 2 of those to pull it back. Times distance squared. All right, well, I need to think about the distance. When I pull back my machine, when I pull back my slingshot, I happen to pull it back 75 centimeters approximately, and that's where I'm shooting from. So if I have 75 centimeters, I need to convert it to meters and then plug it in. So 75 centimeters is 0.75 meters. That's what's going into my equation. So the potential energy of the beanbag in my particular case, or what is at the end of my band, is going to be 1/2 times 53.34 times 0.75 squared. So I end up with a potential energy of about 15. It's really 15.001 or whatever on my calculator. However, I'm going to round it to 15 because it ends up being in the thousands. All right, so that's my potential energy. Potential. As you guys know, because you're really good at knowing what potential energy is, potential energy is all really good, but I really, really, really need to convert it to kinetic energy so that we can get the ball rolling. Haha. Alright, so kinetic energy. Another thing that you guys know a little bit about, but again, the equations are a little bit iffy for us. So, theoretically, energy is conserved in a system. So the potential energy something had is equal to the kinetic energy. And sometimes you have part potential energy and part kinetic energy, but basically the energy in the system remains constant. So I already found the potential energy of my slingshot apparatus. Now I want to find the kinetic energy of my slingshot apparatus. So I need to know a little bit about the formula for kinetic energy. The kinetic energy formula is 1/2 mv squared. So the mass times the velocity squared. Well, I know you're sitting there going, well, potential energy, the potential energy was 15, which means the kinetic energy is 15. So why do I have to bother calculating anything at all? I already know my kinetic energy. But what we care about is the velocity. We don't know that yet, but we can use the information we have to find the velocity. So, kinetic energy is going to be equal to 15. I'm plugging this equation in down here. Equals 1/2 the mass. Well, somebody and I, we actually massed the beanbags, and we found that it was about 85 grams. So that means, since we're using our kinetic energy equation, we need to convert it into kilograms. So it was about 0.085 kilograms times velocity squared. I don't know velocity, so that's going to stay a v. Alright, so now we just need to solve. So we need to think about what we're going to do. If you want to, you can divide both sides of the equation by 1/2, or you can multiply them by 2. Either way, 15 divided by 0.5, or 15 times 2, we end up with 30 equals 0.085 times velocity squared. Divide both sides by your 0.085, and you're going to end up with about 3,529.41 equals velocity squared. Take the square root, and that's going to get me my velocity. So my velocity is going to be 59.41 meters. So now that I have my velocity, I need to think about what that actually means in my situation. This whole 59.41 is the velocity of a specific thing, not necessarily what I can go ahead and throw into my position equations right away. So that leads us to our next topic. Think about Angry Birds. When you are playing Angry Birds, you are pulling your band back at an angle. Think about what you guys are doing when you were doing your testing. You are pulling your band down at an angle. I didn't see anybody pulling straight horizontally with their band. Not even the group who has their big like turtle thing going on. So we have to think about the components of velocity. We found our velocity to be 59.41. But keep in mind that that velocity really is talking about a velocity that's happening at an angle. It's not a velocity in just one direction. So this leads us to go back to right triangles. So if we look at our velocity vector has both an x component and a y component. If we were going to write some equations for our x position and our y position, we actually have to know the velocity for just those two parts. So yes, I know that the velocity at this angle is 59.41. However, I don't really care so much about that. I need to find those individual components. Right triangles, that leads me to trig. Yay! So think back to our vector stuff. If we knew angle theta, then we could use cosine and sine in order to find the two components of the velocity. So if we were going to talk about the x component of velocity, the x component of velocity is the velocity, the total velocity overall, times the cosine of angle theta. The y component of the velocity is the velocity total times the sine of angle theta. So this is important. Not very many of you guys have been very consistent on this, and you need to be consistent on it. You want to have some marker or something to let you know what angle you're pulling back at, what angle it leaves your device at. This is something some people have gotten really good at, and those are the people who can duplicate their results. So let's figure out what your angle is. You're going to have to know that before you go into these components of velocity. So for my particular machine, my example, look, warning, warning, this is my theta, not yours. My theta is 30. Not going to lie, very few of you are going to have an angle degree of 30. Most of you guys are going much, much deeper than that. So my theta happens to be 30, and I know my velocity, so I can find my components of the two velocities. So for the x component, I'm going to do 59.41 times the cosine of theta. And for the y component, I'm going to do 59.41 times the sine of theta. Alright, so when I do that, I should get my two calculations. It looks like I get my x component to be 51.45, and I get my y component to be 29.71. Just using my calculator, making sure it's in degree mode, because I use degrees for my angle theta. Now, think about what my two numbers represent. 51 and 29. My velocity is a lot stronger in the x, or it's a lot bigger in the x direction, because an angle measure of 30 is not very steep. It's not very high. So my velocity is much bigger in that x component of it, and the velocity is smaller in the y component of it. Again, your angles are going to be different, so your component velocities are going to look a little bit different too. So what are you going to do with these velocities? Why do they really matter? At the end of the day, it leads us finally back to our position equation. At the beginning of this project, we had you guys look up the kinematic equations, looking at the motion, and you guys found a lot of equations associated with it. And that's because there are equations that are reflective of only things happening in the horizontal direction, and then there are equations that are solely responsible for the vertical direction and the vertical components of the motion. So we need to look at each component separately as well. That's why we found those two velocities, the x velocity and the y velocity. They're going to help us write our equations. So if I want to think about a really general equation for any position and then apply it to the horizontal position, I could say that, oh, you can find your final horizontal position if you take your initial horizontal position added to the initial horizontal velocity times time, added to 1/2 a in the horizontal direction times t squared. This equation should look really familiar to you, except you see all these x's in here. So let's think about the horizontal position of our beanbag and the horizontal parts of our beanbag's path. Let's see if we can't simplify this equation a little bit. When you're measuring how far your projectile has gone, you're usually starting at the start line. And so for the initial position, generally that's 0. So for us, we probably don't need to worry about that. The other thing that we can cancel out is acceleration. Think about your beanbag as it leaves your machine. Is it continually accelerating, or does it accelerate at all in the horizontal direction? No, it only gets a vertical acceleration. So that last term cancels out as well. So we can basically say that, if I want to find the horizontal position of my beanbag or of my thing, I just need to do the initial horizontal velocity times time. We've actually used this equation a lot. It's a nice, easy little linear equation. And I'm going to apply it to my particular machine. I found my initial velocity in the x direction, so my specific equation is x equals 51.45t. Now I want to hang on to this equation, and I'm going to use it to do some calculations. Those will be different for whoever's doing them, just depending on what your particular goal is. Do you want to figure out how long it takes to do something? Do you want to figure out where it's going to happen horizontally? And it might actually also be vertically. So let's look at the vertical position next. You're going to use these two equations in conjunction with each other because both of them will have one commonality. Both of them will have time. The vertical position of your beanbag has an equation that starts out really similar to the horizontal position of the beanbag. And it's one that you all should be incredibly familiar with. It is the final vertical position is equal to the initial vertical position plus the initial velocity in the vertical component of it times time plus 1/2 at squared. Now, let's try to cancel stuff out like we got to cancel stuff out in the other problem. So initial position. Not very many of you guys are launching exactly from the ground, and so a lot of you guys are going to have an initial vertical position. The other thing you can think about is acceleration. There is always acceleration in the vertical direction. There's always acceleration due to gravity. Remember, that is negative 9.8 meters per second squared. So we can plug those things into our equation as we're plugging in our initial velocity, and we'll be able to see what our equation looks like. Yeah, it's a little bit bigger, but remember, you have 4 tools for solving quadratic equations. So, for my machine, I know that I can calculate the final vertical position of my beanbag using some information from my situation. When I pull my band back, I actually start, or it leaves at a initial height of about 0.8 meters. And then I know my initial velocity components, the vertical component of it, is 29.71. So I can add that in, times t. And then I know that the acceleration due to gravity on Earth, in general, is negative 9.8. Times 1/2, I'm going to end up with minus 4.9 t squared. So that's an equation that I'm going to definitely want to use a lot. I'm going to want to know about the vertical position of my beanbag at various times. Think about those hoops that you have to get through. It's important for you to know how high your thing is, as well as how far it is when it is that high. A lot of you guys are becoming too high too early or too high too late. You're not getting it through those hoops. That's not getting you a lot of points. So hopefully this was helpful in sort of stepping you through the different things you're going to need to think about. There are more kinematic equations, and you can check those out in that Game Rules and Need to Knows research document that we did. And once you get those equations, you can just apply these things you already know to those equations. And see if you can't maybe increase the accuracy and precision of your trials, because you don't have unlimited tries on any of the 3 game fields.